Okay, so I'd like to spend a minute going over this problem that I got stuck on during class the other day. So this is the first situation. You have the bullet come in, let's call that V initial, and this is the block, wooden block. Here's big M. Okay, so here comes the bullet. It goes in and it embeds in the block. The block is stationary. It's in a vise, or it's bound where you can't, it won't move. So the bullet goes in and it embeds in the block. And it goes to a depth, I'll call that D1. Okay? So from this, that initial kinetic energy is turned into the stopping energy. So you have it turned into friction, stopping the bullet, and that is 1/2 mv initial squared is equal to F D1. So that's some, average force. I'm just going to call it F, average force on the bullet that stops it in the material. In the second situation, here's the bullet coming in, same initial velocity, okay? Only this time, big M is on a frictionless surface. So the bullet's going to enter and then they're both going to go off like that by conservation of momentum, okay? So here comes the bullet, and then this is stationary. At some later time, you have, I'll try to fit it in down here, the big mass, and the bullet is embedded in this, and I'll call that little distance D2. Okay, and this is some V final based on the final velocity of the bullet block system. Okay, this is the only thing we know from the first equation, or from the first situation. That kinetic energy was turned into friction. There was some work that went into stopping the bullet. Okay. In this case, this is definitely an inelastic collision. There's energy lost. Where is the loss in the second case? In the second case, we have conservation of momentum. So mv initial is equal to, that's little m, is equal to little m plus big M V final. Okay? Because in the inelastic collision, the initial momentum of the system is just mv initial. The final momentum of the system is little m plus big M times some final velocity. But we also have that the energy loss in this case, which is going to be 1/2 mv initial squared minus 1/2 little m plus big M V final squared is equal to F D2. We're making an assumption that the force in both of these cases, so sort of an average force, is the same. That's a pretty strong assumption. Would this work? I don't know. I'd have to do do an experiment, but I don't know. We're assuming a lot of stuff here. Okay, so you got that initial kinetic energy of the bullet, the final kinetic energy of the bullet block system, and the difference in those two is what was lost in stopping that bullet in the block. All right, so I have these three equations. Okay? So look here. 1/2 mv initial squared is FD1. Well, I can make a substitution for this, and I also know that V final is little m plus big M over little m. V final is equal to little m over little m plus big M times V initial. So I'm going to write that down. So I have that V final is equal to little m over little m plus big M times V initial. Okay? I think that'll get us there because we have a way to substitute in here and here, get rid of F, and find D2 in terms of D1. So let's do that now. Okay? 1/2 mv initial squared is FD1. So I'll get rid of, I'll write it down here. So I'm substituting here. This is FD1. So I get FD1 minus 1/2 little m plus big M times V final squared. V final is equal to this. Okay? So you get this squared. You get little m plus big M. No. Substituting here. Little m over little m plus big M squared times V initial squared. That's substituting in V final up here. Okay? I'm going to go ahead and all of this is equal to FD2. FD2 from here. The board's so small I can't move things around the way I want to. That's my excuse. All right, so I'm going to work with this equation now. I'm going to leave this up here. So rewriting this, I'll clean it up a little bit. I get FD1 minus. This works out to be M squared divided by little m plus big M, and I still have the 1/2, times V initial squared, and that's FD1. That's FD2. Okay, from down here. This is FD1 minus 1/2, all of that stuff, and that equals FD2. Because you square this out and you get an M squared, and then you get cancellation for the M, the little m plus big M in the denominator by this one. Okay? So look, I now have FD1. I can factor out a 1/2 MV initial squared, and I'm left with M over little m plus big M. Okay? and that equals FD2. But 1/2 mv initial squared is FD1. So I have FD1 minus FD1 times little m over little m plus big M. That equals FD2. All these F's cancel. Okay? Factor out a D1. Keep wanting to write an equals. Factor out D1 and I get D1 times 1 minus little m over little m plus big M. And that equals D2. The F's cancel. Factored out a D1, that looks right. So this gives me D2 is equal to big M over little m plus big M times D1. And that's it. Works out to just be a ratio between the total mass of the mass of the block divided by the total mass of the system times D1. All right, good. Okay, let's go ahead and get started. So are there any questions on the homework specifically? I'm going to go over the Chapter 9 homework. Are there any questions on any of the other problems? I can't see your faces, so I guess that means no. Any questions on anything else? Once again, I can't see the chat. I can see it in a minute, but so speak up.
No questions.
Okay. Okay, so I wanted to look at these Chapter 9 problems. Oh shoot, I got another laptop in here for the problems. Okay, here we go. Okay, so number 1 is about a baseball. If you can open up in WebAssign the problems so I don't have to read them, but this is similar to the one that I did in the explanation of collisions and so forth and impulse. So this is an impulse problem. So for impulse, the change in momentum is equal to F, let's just say average, times delta T. Okay? So delta T in this case, they give you some number for how long the ball is in contact with the bat. And I think the ball is coming in like this. So it's M, I'll call it MB, and it has some velocity, all right? So that's its initial momentum is M times its initial velocity. Then it strikes the bat, and I think it's a pop-up, and it goes off at some, MB doesn't change. I think they use 145 grams. So it's a pop-up, and that's the final velocity. So you take delta P, which is P, remember these are vectors, P final minus P initial, and that's going to equal F average. And you have to divide this by delta T. Okay? So you're going to get an answer that has an X component and a Y component, obviously. I think that's obvious. That change in momentum is going to be, along here somewhere. Okay, it's V final minus V initial, so it's Yeah, it's this way. Okay? So, that's problem one. Any questions on that? You have the time, you can calculate the change in momentum. That's going to give you the average force. Number two. Okay, the front of a car is designed as a crumple zone that collapses to absorb. Cars traveling at 29 meters per second stops uniformly. All right, in 1.2 meters, how long does the collision last? All right, so if you know that initial velocity, this is from what we did previously. I mean, you know the initial velocity, it's uniform, you know the initial, and you know the distance, so delta x is equal to whatever it is, 120 meters. You can calculate the acceleration. So what is the magnitude of the average force on the car? You can do that through work. The average force is equal just to the work divided by delta x. Okay, so it had a certain amount of kinetic. There's several ways you could do it. It had a certain amount of kinetic energy. Okay, you can figure out the work done, the change in kinetic energy, and divide by delta x, and that's the force. That's the average force. All right. What is the magnitude of the acceleration of the car? Well, I did that in the first part, okay? You can do this as an impulse problem, looking at the change in momentum, but I don't think they give you the time, okay? Well, yeah, you have to calculate the time in part A, right? Okay, so you can calculate the time in part A, and then from the time you can look at the change in momentum, and that's the force times the time. Maybe that's the best way to do it. You can calculate delta t, that's part A, and then this is part A. Then for part B, you have delta P. It's 1D, so delta P is F average delta T. Okay. Yeah, that's probably the best way to do it. We can do it the old-fashioned way with work, but all right. Stop me if you have a question. Number 3. Okay, so they have a car traveling and it hits a truck. So these are nice collision problems. So you know the initial velocity of the car, and it crashes into a truck. All right. Okay. So in this case, here's the car, here's the truck. All right, the car is, speeding up, the truck is also moving. So this is V car initial, V truck initial, and you can calculate the initial momentum of the system. Then after the crash, you've got the car and the truck are connected together. So here's the car, here's the truck, and I think they give you the final velocity of the car, but that's going to be the car-truck system. So V final. So you can calculate P This is an inelastic collision or perfectly inelastic. P initial is equal to P final, okay, of the system. So the initial momentum is going to be the momentum of the car plus the momentum of the truck. The final momentum is going to be mass of the car plus mass of the truck times that final velocity. Okay? That's conservation of momentum. Alright. Well, they say, what is the velocity of the truck right after the collision? So, I mean, they're stuck together, right? Maybe not. In the drawing, it looks like they're stuck together, but it really doesn't matter. It really doesn't matter because this is what you need. So if they give you the final velocity of the car, then you can calculate the final velocity of the truck because the momentum is conserved. Okay. What is the change in the mechanical energy of the car-truck system in the collision? So this collision definitely does not conserve kinetic energy. So if you calculate the kinetic energy before the collision, you calculate the kinetic energy after the collision. So this is initial, this is final. Okay, let me change this up a little bit. Since the way they worded it, it looks like they're not connected. Here's the car, V car final, V truck final, okay? So if you calculate the initial kinetic energy and look at the final kinetic energy, then that difference is equal to the change in kinetic energy for the system. In inelastic collisions where you have losses, you have a decrease in kinetic energy typically. Any questions on that? Okay. Questions?
So, when you say it's the kinetic energy is not conserved, does that mean it's just like transferred to like heat, like thermal? Is that what you mean?
Yeah.
Like it's transferred.
Yeah, absolutely. Absolutely. It's transferred to something. I mean, maybe parts flew off the car, it transferred into crumpling, wherever it was transferred. Okay? The momentum is conserved. This is why back in the old days of racing, like let's say open wheel racing like IndyCar and stuff, they thought that you made the cars stronger and that would be safer. But actually they make the cars a lot lighter now. They make them where they fly apart because you're losing kinetic energy. It's a way to lose kinetic energy instead of transferring that kinetic energy to the driver. So yeah, kinetic energy is lost in the collision. Okay, number 4. 4 railroad cars are coupled together and coasting. So they've got a V initial towards the south. A very strong but foolish movie actor riding on the second car uncouples the front car and gives it a big push, increasing its speed to 4.65 meters per second southward. The remaining cars are continuing moving south now at 2 meters per second. Okay? So, let's look at initial. So 1, 2, 3, 4. They're all moving at the same velocity, south. Okay? So you don't know this initial velocity. I would say the mass of the person that's on the train is irrelevant. The train car is, what, 10 to the 4 kilograms? I don't think they give you the mass of the person. Okay? Okay, so the final, you have 3 cars, and they're moving at 2.0 meters per second south, and then this one is moving faster, right? Is that okay? 4.65 meters per second. All right. So what you have to look at is the change in momentum. I'm assuming that all the cars, have the same mass. All right. And in part A, you're asking for the initial speed of the 4 cars. Okay? So by that internal force, since this was an internal force on the system, the momentum of the total system did not change. Okay? And so you've got the final momentum, which you can calculate. The initial momentum, the only unknown is V initial, and you can calculate that. Okay. Part B, by how much did the potential energy within the body of the actor change? Well, that's a weird way to say it. But he had to do a certain amount of work to uncouple the cars. So if you look at the change in kinetic energy, then that's how much work he had to do in a negative sense, okay? Just like the previous problem, look at the change in kinetic energy. The kinetic energy before and after, that gives you the change. That's how much energy he put into the system. So he lost that much energy. That's goofy, but okay, we'll live with it. Okay, a 7-gram bullet, when fired from a gun into a 1.10 kilogram block of wood held in place or held in a vise, penetrates the block to a depth of 9.2 centimeters. So what kind of information is that going to give you? That's going to give you the average force of the bullet in the block, right? Okay. So you can calculate that because if you know the depth that it penetrated, okay, is that right? Let's see. Oh, let me think about this one for a second. No, you don't know the initial velocity. Okay, hold on. Geez, I may have to think about this one for a second. I thought about it before, but okay, let's see. So all right, so let's say the velocity of the bullet is number, what am I up to? Number 7. Okay, so this is a one-dimensional center of mass problem. A rod of length, whatever it is, has linear density given by, my numbers are lambda. I'll just put it as lambda equals A plus B x. Okay. So first off, they're asking you for the mass. How do you find the mass? Well, the way you find the mass is take the integral from 0 or wherever it starts. It says it's a length 32 centimeters. Mine has, I'll just use L. Okay. 0 to L of lambda dx. All right. Because dx is your little bit of length, and this lambda is equal to mass per unit length. And it's in the form A plus bx. So the total mass is equal to that. Part B, find the center mass. Well, for the center of mass, if you watch the center of mass lecture that I did, x center of mass is going to equal 1 over big M times lambda x dx. Because this plays the role of the mass, the little bits of mass, and that's the position. And this also goes from 0 to L. Watch the lecture that I did calculating the center mass of the plate, and that's it. Okay, number 8, last one. But I got to go back to the other one. I'll let you know on the other one. 1.6 kilogram, that's my number. Block rests on a table over a large hole, as in the figure. A bullet with an initial velocity is fired upward and remains in the block after the collision. The block and bullet rise to a maximum height 23 centimeters. Calculate the initial velocity of the bullet from the information provided. Okay. So in this case, this is one I know how to do, I think. In this case, here's the block. Call it big M. Here's little m coming in, striking the block. Okay? So what you can do is, this would be calculate the initial momentum, P initial. Alright? That's, since it's an inelastic collision, after the collision, you've got big M and little m is embedded in big M. And it's risen up to some height h. Okay, I drew it goofy, but let me draw it better. Okay, it's risen up to some height h. All right. Momentum is conserved, so if you figure out the final momentum, P final is equal to m plus big M times V final, and that's going to equal P initial, all right? But you don't know V initial over here, but you can find it because you know the height to which it rose. So from 1D acceleration equations, you can calculate this V final. That was the initial velocity for the system. Then from that you can calculate this, that equals this, and you can get the initial velocity of the bullet. Okay, number one. So number one, you have a baseball. This is like the one that I did in the lecture that I did, I think, on impulse and momentum. So you have a baseball coming in at some initial velocity, strikes the bat. Here's the bat. Okay. Strikes the bat, it's a pop-up, and you have the final velocity. All right. So the average force, this is F average, times delta T is delta P. Man, my writing's terrible. Delta P. Okay, so you know delta P, you can look at the change in momentum. That's MV final minus MV initial, and divide by delta P, and that'll give you the average force. Remember that it's a vector, so you're going to get two components. You're going to get some change in force that is, this way, whatever way it is. Okay. So you get an X component and a Y component for the average force. Stop me if you have a question. All right, number two, what was number two? Oh, this is the car is designed as a crumple zone that collapses to absorb the shock of a collision. So they give you the initial velocity of the car and it stops uniformly in 1.2 meters. How long does the collision last? So you can do that from a 1D, that's an impulse problem. You can look at the change in momentum is equal to F delta T. Okay? Because you can figure out the force, you know the mass, you can figure out the acceleration, you can figure out the force, then you can figure out how long the collision lasts. So part B, what is the magnitude of the average force? Once you figure out delta T, you can get the average force and so forth. Lots of ways you can do this one. What's the magnitude of the acceleration of the car? Well, you know the initial velocity. No, you don't know the initial velocity, but you can figure it out. And then you can figure out the acceleration. Okay. Well, you can figure out the acceleration right from the beginning, I think. No. Yeah, they give you the initial velocity. Okay. You can use the 1D motion stuff with this and momentum, change in momentum. All right, the next one, number three. Number three is a conservation of momentum problem. So for number 3, there's a car. Here's the car. I'll call this V car initial. It's 1D. I'll leave off the vector symbols. And then there's a truck. And it has VT initial. Okay. So this is the initial situation. Then the car crashes into the truck. All right. So after the collision, you have V car final, and here's the truck, V truck final. So this is P initial of the system. This would be P final of the system. You know these masses, and you know this, you know this, you know this. You can figure out the final velocity of the truck. All right. Then part B says, what is the change in mechanical energy of the car truck system? So the change in mechanical energy is going to be that change in kinetic energy. Momentum was conserved, but kinetic energy is definitely not conserved. You had a collision, some of the energy went into smashing the cars together, and who knows, parts flew off, okay? So you look at KE final minus KE initial. That's going to give you something negative, and that's going to equal that change in the energy of the system. Okay. Any questions on that? All right. Number 4. Okay, this is the railroad car problem, and the person, this is another conservation of momentum problem. So you have 4 railroad cars that I'm assuming are equal mass, and they're all traveling along at some V initial. They all have the same, it says south, so I'm going to draw it this way. They're all traveling at this initial velocity, so you have some initial momentum here. Then there's an internal force, and I think you can ignore the mass of the person. All right, so you have V final of these 3. They're moving in this direction. They slow down. This one speeds up. V final here of this one. I'll call this V3 final. That's 3 cars. And I'll call this V1 final. That's 1 car. Okay? So now from this, what's part A? Find the initial speed of the 4 cars. Well, here's P final. P final equals P initial. You know these velocities and these masses. You know these masses. You can calculate V initial. Then kind of a silly question. I don't know, maybe it's not silly. It seems silly right now, but by how much did the potential energy within the body of the actor, the person, change? Well, if you look at the difference in kinetic energy here, so the total kinetic energy, initial, and then over here you have KE final. that difference is going to be how much energy that person had to put into the system. Okay? That person lost that much energy. So that's what they're asking. If you look at the difference between these two, that's going to be the change in the potential energy of the actor or whoever he is. Number 5. Okay, number 5 is the one that I got stuck on, so I'll skip that for now. Number 6, I'll let you know on that, don't worry. Number 6, a uniform piece of sheet metal is shaped into the, as shown in the figure. I don't think you'll have any trouble with this. Each little cell, the center of mass of each little cell has a coordinate. You know its mass. Mass times coordinates divided by the total mass. That's center of mass. Remember, center of mass, X, center of mass is equal to 1 over the total mass times the sum of each little individual mass times its position. Okay? And remember, these X coordinates are at the center of each little cell. If you have a square, that's the center. Okay? And you have to do the same thing in the Y direction, but I don't think you'll have any trouble with that. Number 7. Number 7 is the non-uniform mass rod. So they give you a mass per unit length. Lambda. And that's of the form A plus BX. So to find the total mass in part A, you integrate from 0 to L of lambda, I'll just write it as lambda dx. Summing up over all the little positions, because this is mass per unit length, you're summing up lambda. Okay? Then for the center of mass, X center of mass, where we had the summation before, you now have an integral, 0 to L of lambda x dx. Okay? You have to have the little bit of mass, which is lambda dx, and the position x. Because dm, if you think back, if you watched my center of mass video, dm is lambda dx. Okay? That's that little bit of mass, that's lambda dx, and then you multiply by x. And integrate. And don't forget, when you find the center of mass, it's a weighted average, so you have to divide by the total mass. Stop me if you want to. Are we to the last one already? Wow. Okay, so this is a conservation of momentum problem. You have a projectile that's, here's big M, it's sitting on some table. Here comes a projectile V initial. All right. It enters the block and sticks. The block, and it's not a very consistent block. The block and little m, this has little m. Okay? The block and little m rise up from the table to some height h. Okay? The initial momentum in this case, the initial momentum is m, just mv initial. All right? The final momentum, which is going to be, let me write this as P initial. Okay. P final is going to equal little m plus big M times V final over here. Okay. So if you can calculate this by knowing that it rose to a height h, you can do that from what we've done with work energy and potential energy. Okay, you will be able to calculate this. You get the final momentum, that equals the initial momentum, and then you can solve for V initial. You have to figure this out first by knowing that mgh, okay, is equal to the initial kinetic energy.